For the next half hour, I'm going to tell you a little bit about Shasta. Shasta is something we've been working on for the past 5 or so years, and it is finally almost here. It'll be shipping next quarter. So we are obviously pleased as punch that it's been chosen for all 3 of the announced Exascale systems. So we're really excited about that. But we don't really view this next era about a particular machine. In particular, it's not about computation. And Rick just did a fabulous job of telling us why. Right? The world of the future is not flops. It is combined heterogeneous AI analytics and simulation, and it's a world where we're increasingly dealing with massive amounts of data. This is affecting the enterprise space as well as the hyperscale and obviously the HPC community. So when we started thinking about designing Shasta, 4 or 5 years ago, we looked out at a bunch of trends that were happening in HPC that kind of informed the design. The first is that CMOS performance is plateauing. We're starting to see this Cambrian explosion of processors, and so we had to build an infrastructure that was good at heterogeneity, at lots of different types of processing, and particularly, in addition, deal with processors that are getting hotter and hotter. We're already feeling like we tripled the amount of power that could go into our per cabinet, and we're already feeling shortchanged because we're getting processors now. We bid processors that are above 600 watts. We've seen processors on roadmaps that are above a kilowatt. So this is one of the big things going on. I don't need to talk about simulation, analytics, and AI. Rick just did that for an hour, but this is obviously a big trend going on. Cloud computing is hard to ignore as well. There are a lot of great things about cloud computing from a usage model that make it very attractive. There are some not so great things about cloud computing which make us think that it's not going to take over the world, especially for capability high performance computing. We think a hybrid cloud model makes a lot of sense. But one thing undeniably cloud computing has done is it has raised the expectations for the type of software environment that people expect in terms of a very flexible, open, dynamic software environment. And then lastly, there's some interesting things going on in just some of the base technologies where memory is finally starting to catch up partially to the performance gains that computation has seen over the years with the move to on-package memory. And there's some really interesting storage technologies coming down the pike with non-volatile memory, carbon nanotubes, phase changes, et cetera, which is shifting everything to the left or the right depending upon your perspective. Tape is giving way to disk for archive, disk is giving way to flash for high performance scratch storage, and then we've got these new non-volatile memory technologies coming in to fill the gap between memory and flash. So Shasta was really designed to try to react to all of these trends, to try to run workloads that are much more heterogeneous and multi-tenant than they used to be. At a very high level, what we try to do in the hardware infrastructure is make it very flexible, able to accommodate these new hotter processors, and have the hardware infrastructure last for at least a decade. We're trying to support a wide variety of processors. I'll talk quite a bit about Slingshot, which is our next generation interconnect. That's probably the biggest thing we did in the hardware side of things. From a storage perspective, we'll see a kind of a next generation of storage coming online where we can kind of pull the storage into the high-speed fabric. And then lastly, a complete revamp of the software infrastructure. So a big step away from what we've been doing for the past 20 years or so in HPC software stacks to try to be much more cloud-like. So in the infrastructure, many of you probably know this, but we've got 2 different cabinet types. We've got a dense liquid-cooled scale-optimized cabinet, and then a bog-standard 19-inch cooled, or 19-inch air-cooled kind of infrastructure. And whereas in the past, our CS line had a standard interconnect, a standard software stack, and a standard packaging, and our XC line was, optimized liquid-assisted cooling and a custom interconnect and a custom software stack. Now those things, those associations are broken, and you can have the exact same software stack and the exact same interconnect on either platform. So it really just becomes a packaging choice. The fact that we're seeing a variety of processors coming online is probably best illustrated by the fact that the very first 3 announcements we made for Shasta systems had 4 different types of compute blades. The NERSC system had AMD Rome compute blades built with 2-socket standard kind of CPU nodes, the same sort of thing that we've been using for a long time. It also, in the same system, had a compute blade based on dense GPUs with 4 NVIDIA Tesla GPUs and an AMD EPYC CPU, kind of a 1-to-4 tightly interconnected node. Then the Frontier system that's going into Oak Ridge had a very similar looking node, but based on AMD GPUs, where you use AMD's inter-GPU interconnect that also talks to the CPU in a coherent way, but otherwise looks quite similar to the NVIDIA-based node. And then there's the Argonne system, where there's a big cloud and there's some Xeons in there and some Optane memory and some Xeon Phi and a bunch of network ports. And maybe at some point we'll be able to tell you a little bit more about what that node looks like. So 3 systems, 4 different nodes, and we see this sort of, this variety growing in the future. So I want to talk a bit about Slingshot. I'm kind of a network architect at heart, and so I love talking about Slingshot. It's our 8th generation network. We've been doing this a long time. In the past, we were the first to do adaptive routing back in 1996 on the T3E. So it's been about a decade later. Other people started doing adaptive routing. We pioneered high-radix switch designs back in 2005 with the YARC 64-port router, and then invented the Dragonfly topology. I think I'm probably more excited about Slingshot than I am about any of the previous networks we've done. It's a kind of state-of-the-art network from speeds and feeds, but not particularly differentiated here. So it's got 64 ports, so more ports than an InfiniBand network per switch, but otherwise looks a lot like HDR InfiniBand or the latest generation of 200 gigabit Ethernet. With this, we can build a low-diameter network that can scale to over 250,000 endpoints with just 3 switch-to-switch hops. So you can get a very low-diameter network, which is good for performance. It's also good for cost. It is Ethernet compliant. So this is the really weird thing. I mean, what the hell are we doing here? We're building an Ethernet network. In the past, you either had Ethernet for standards-based networking and interoperability in the data center, or you had an HPC network with much better performance, and you had to choose between the two. We're realizing that Ethernet is the future, and so we designed Slingshot to be Ethernet. But underneath the covers, it is every bit a state-of-the-art HPC network. But what this means is that we can just take a standard third-party storage device that talks Ethernet, hook it directly up into Slingshot. You can use anybody else's commodity NIC if you want to, hook it up into Slingshot. You can hook up directly into the Ethernet data center. So from this whole era of data interoperability, this is really important. We do a great job of adaptive routing. We've been doing this for a long time. We haven't done quality of service in the past, so this is something where we've actually been behind other networks. But Slingshot has great QoS mechanisms. I'm not going to go into the details talking about that today, but it allows us to get really, really high performance at scale and then basically layer on different virtual networks onto the physical network with different performance and functional characteristics to separate known different categories of traffic. The crown jewel of Slingshot is its congestion control. This is really, really innovative stuff. I'm just super excited about what the team has done here. There's been congestion control like ECN, data center congestion control networks out in the wild for a decade or more than a decade. ECN and similar sorts of mechanisms are not very good for HPC. They're slow to converge, they're fragile, they're hard to tune, they just don't work well on dynamic HPC workloads. Slingshot takes an entirely different approach where you're not just, it converges much more quickly. It's much more stable across a variety of different workloads in ECN, but most importantly, during the time it's trying to converge, it's basically keeping track of everything that's going on in the network and preventing head-of-line blocking for all the fabric, and across all the fabric. And I'll say a little bit more about this. But what it leads to is not only low mean latency, but low tail latency as well. And this is really important if you've got scalable apps that do any form of synchronization. We worked with an Ethernet network company that shall remain nameless at the moment to create a new wire protocol between chips. So this isn't the special sauce that's inside the chip, but it's the protocol used to communicate between chips. We call it HPC Ethernet because it's basically an HPC-like protocol, but it's designed to be very sympathetic to Ethernet, so very easy to convert from standard Ethernet frames into this optimized protocol. And so we can speak standard Ethernet at the edges when needed, but then everything inside is this optimized protocol. It does things like reduce the minimum frame size and get rid of the inter-packet gap and reduce the headers. It uses credit-based flow control instead of stop-go, so it's more efficient. This chart on the right, I'm not going to spend a lot of time on it, but it's basically just an analytic chart showing the messages per second you can get versus the message size. And basically what we see is that on the bottom here we've got 100 gig Ethernet with Rocky. And what you can see here is that at 256 byte messages you get a certain throughput, and when you drop down to 8 byte messages the throughput goes up, but not very much, because it's got big honking headers that make it very efficient for fine-grained traffic. In contrast, same signaling rate with EDR InfiniBand, similar message rates at 256 bytes, but much more efficient at 8 bytes if you look at that blue line. Basically, InfiniBand is a well-designed HPC network. The Aries network, which is a 14 gig, so more of an FDR generation of network, looks very similar at 64 bytes, but again, you can see it's much more efficient for fine-grained stuff. And then if we look up at the top here, the two 50 gig signaling networks, HPC Ethernet, which Slingshot uses, and HDR InfiniBand are very similar. Very slight differences, but effectively they're both good HPC networks. So this is what it does from an efficiency perspective. It also has a bunch of resiliency benefits. There's a low latency forward error correction. You can read more about that if you look at the 25 gig Ethernet consortium, because Broadcom recently contributed this to them. It uses link level retry to tolerate transient errors, and it also uses lane degrade to tolerate hard failures if you have a laser that goes bad or a pin that gets bent, that sort of thing. So it's an efficiency and resilience benefit. So congestion control, as I mentioned, is kind of the crown jewel. Basically what happens is inside Slingshot there's a bunch of sophisticated tables in hardware, no software is involved, and it tracks every single packet that's in flight between every pair of logical endpoints in the system. And it's very quick to detect when there's congestion occurring in the network. It gives you very stiff and fast back pressure to sources that are contributing to congestion. It can figure out if you're a victim of congestion or a contributor to congestion. Stiff arms the people that are contributing to congestion, but does it in a way that doesn't block anybody else, even if they're on the same traffic class or the same virtual channel. And what you get from that is basically not chip-wide, but fabric-wide freedom from head-of-line blocking. The bad guys get stopped, other traffic can pass it, and so you get this great performance isolation between workloads. This is really fundamentally different than other congestion control mechanisms that have been done in the past. And as a result, what you get is something that's very stable across a wide variety of traffic patterns, and you get this great performance isolation. Quality of service gives you performance isolation if you can put two different workloads on different traffic classes. But most of your workloads are going to be running on the same traffic class, and that's where this kicks in. So I'll show you just a couple of performance slides here. This is a simulation. We've reproduced that now on real hardware that we've got in-house, but this is a simulation of several thousand nodes with 3 different jobs running. This is the Slingshot network, but with the congestion control turned off. You'll see something very similar in an Aries network or an InfiniBand network. And what we see is terrible performance interference between applications. We've got a blue job which is doing all-to-all communication. It's well behaved. It should be getting 200 gigabits per second per endpoint, which is 100% of peak. We've got a red job which is doing halo exchanges and then synchronization. It's latency sensitive. You have to completely finish one before you pass the synchronization and go on to the next halo exchange. So we care about latency of the tail latency. And then there's the green meanie, which is causing a bunch of random hotspots in the network and causing congestion. And early on, the blue and the red workloads get close to 100% of peak, but then the green workload kicks in, starts creating congestion, all hell breaks loose, the blue workload gets terrible performance, and then the latency sensitive workload gets really terrible performance. The first epoch goes, and it takes a while for the last packets to show up. And the second epoch, it's getting really bad performance, and then it just takes forever, like over a millisecond for the last packets to show up because they're stuck in traffic behind the green. Okay, so this is the performance interference that we get on today's network. Turn on the congestion control and we get this picture. We get, they're all in the same traffic class. They're running in a way that would normally interfere with each other. But the congestion controller shuts the green guy down. He actually gets slightly better performance, but his performance is limited by the egress bandwidth. There's nothing you can do to really help the green workload. But now the red and the blue workloads go along without interference. So we're pretty excited about this. One of the things we think the world needs is some better benchmarks to look at networks and give you better information than you get out of like ping pong latency. You know, I like to joke that the ping pong benchmark is kind of like trying to figure out what your commute into New York City is and going out by yourself at 4 o'clock in the morning and driving the route when nobody else is on the road and saying, hey, it's 20 minutes, great. The reality is that most latency in practice in networks come from queuing latency with congestion and interference with other traffic, not from the unloaded latency. And that's what this benchmark, among other things, tries to do. It was developed with NERSC and Argonne people, some Oak Ridge input as well. It's publicly available on Argonne's GitHub site. And what it tries to do is proxy some actual real-world communication patterns, and it measures the network performance under load, not on an unloaded network. And it looks at both mean latency and tail latency, and then lastly it looks at what happens to good traffic when bad traffic comes along and interferes with you, and how does it deal with the congestion that occurs. So I'll just show you a couple of results from that. This is looking at Slingshot versus EDR Mellanox InfiniBand. Don't think of me, I'm trying to pick on InfiniBand because I could show you the exact same results comparing against the Aries network, and you'd see a similar phenomenon. Mellanox has better unloaded latency, 1.6 versus 1.8. Microseconds in this particular case. Slingshot was not designed for unloaded latency. It was designed for high sustained throughput, which leads to lower latency under load. Then when we throw a congester on the network, we start seeing a very different picture. The Slingshot network has the same average latency, and in the other network it goes up quite a bit. Then we look at the tail latency, the 99% tail. This is the latency at which 99% of the packets are lower latency than this, 1% of the packets are higher latency than this. And you see this an increase on Slingshot, but a huge increase on the InfiniBand. And again, you'd see the same thing on an Aries network or a previous Gemini network at Cray as well. So this is a pretty dramatic improvement in tail latency and interference under load and under congestion. This is one last chart from the GPCNet benchmark. This is showing a bunch of real-world systems. So Crystal and Theta and Edison are Cray Aries-based systems. Theta is the machine here at Argonne. Edison is the machine, the previous generation machine. At NERSC, Crystal is an in-house machine. Osprey, Sierra, and Summit are EDR InfiniBand machines. Osprey, again, is an in-house small system. Sierra and Summit are the large systems at Oak Ridge and Livermore. And then Malbec is an in-house Shasta Slingshot system. So this is showing what's called congestion impact. It's basically the relative performance hit for the traffic under test when you put the congester onto the machine. In other words, how much worse does the congester make the good traffic perform? And it's a log scale, log base 10, so these differences in heights mean something. One thing is very true, that the impact worsens with scale and taper. So if you look at larger system sizes, Theta and Edison compared to Crystal, the impact is much worse. It's worse with taper. If you look at Summit and Sierra, Summit has 100% provisioned global bandwidth. Sierra, like many of the others, have a 50% taper at the global bandwidth, and that makes things worse. We can also observe here that InfiniBand is actually doing better than Aries. If you look at the Sierra and Summit systems compared to the Theta and Edison systems, Aries, the Achilles heel of Aries. I love Aries, right? Does great things, but its big Achilles heel is that you get interference between applications. And one job, you run your job on Monday, run it again on Tuesday, you get different performance because somebody else is doing something to the network. But the takeaway here is that, holy cow, Slingshot does really, really well. So we are, again, pretty excited about this. We think it's going to make a pretty big impact, especially as you get larger and larger systems and systems that do any kind of synchronization. We also think if you look in the hyperscale community, there'll be an impact there as well because they care about tail latency. I grew to really appreciate tail latency during the year I spent at Google. So let me move now to the storage system. One of the things that we're doing, I'll just say one slide on this, is really pulling the storage system onto the high-speed network. So the traditional model that we have today on our XC systems is you've got a bunch of compute nodes attached to a high-speed network. Then you've got a bunch of LNet router nodes, and then they bridge off to an external InfiniBand-based storage area network where you've got largely hard drive-based storage. What we're doing on Shasta is pulling the storage directly onto the network. So the LNet router nodes go away. You now attach the storage directly onto Slingshot. We've got a collection of flash-based nodes that we call Gazelle, and a collection of hard drive-based nodes that we call Moose, which allows you to basically tailor a tiered storage subsystem to meet your demands. So you put as much flash in there as you want to meet your bandwidth and IOPS requirements, and then you fill out the rest with hard drive to meet your storage, your capacity requirements. Some people like NERSC at this point are already flipping over and going to an all flash-based storage system. So you end up getting lower cost because you can kind of tailor the right type of media to the right application, and you get lower complexity and a lot lower latency, which is especially important for small fine-grained IOs. So lastly, let me talk a little bit about the software stack. The XC software stack is a wonderfully scaling, efficient, monolithic software stack. It gets good performance and scalability, but it's not very easy to modify. You know, if you want to interface your own tools or pieces of the software stack into it, good luck. Shasta is designed to have a much more modular and open software stack. So the whole software stack has been refactored. All of the components of the system management are open and documented with RESTful APIs, which means you can use GUIs, command lines, or programmatic interfaces to interface into the software stack. You can interface at whatever level makes sense. If you want just baseline hardware support, you can do that. You can add in, there's a bunch of infrastructure support services, or what typically people will do is have a full platform stack that gives you the full environment. You can kind of decide where you want interface. And you know, for people who want to play around with things, you can even get buildable source now. So if we look at a number of ways and think about our old software stack and our new software stack in Shasta, previously we really concentrated on batch scheduling for basically modeling and simulation codes. Now we're looking at a much more hybrid dynamic scheduling environment with you know, Kubernetes orchestration to be able to put up different sorts of, you know, you want a big in-memory database, you want an interactive analytics section, you want some other batch partitions, you can sort of manage all of those simultaneously. We used to do system partitioning just for HPC jobs. Now we're thinking much more about multi-tenancy and having, so, you know, some partitions for different styles of workloads and sub-partitioning with AI jobs, etc. As I mentioned before, we used to have this very monolithic stack. It was tightly integrated. Difficult when you wanted to upgrade. You wanted to put a new version of the operating system for users. You would have to basically take down the system to do that. Now we have a separate management and management plane and managed ecosystem. You can roll out new versions of the operating system independent without taking down the machine. The management system itself is basically a big Kubernetes cluster with a bunch of services that you know, have redundant failover, etc. So it makes it much more maintainable over time and allows much more seamless upgrades. Again, we used to have very tightly controlled system interfaces, and now everything is being opened up, documented for again, either manual or programmatic access. And then lastly, it used to be really hard to figure out. It is really hard to figure out what's going on in your system from a performance or, you know, correctness perspective when maybe things go wrong or you're not getting the performance you want. Lots of different logs for different sorts, you know, your IO logs and your system admin logs, your mechanical, you know, environmental logs, all in separate places that you'd have to go query. In Shasta, they're all being kind of brought together in a common monitoring infrastructure that allows you to get one-stop shopping to look at all the things going on in the system with abilities to do more, to apply some AI to, you know, introspective AI to the system to help automatically optimize your system plan for the future. So this is just a picture of the software stack. You can see that on the left, you've got the management plane, there's the monitoring infrastructure, and then the set of management infrastructures. They're all running over Kubernetes, so it basically looks like a big Kubernetes cluster. Down at the bottom, you're running across standard network abstractions, which makes it easy to interface using Ethernet to the rest of the data center. And then on the right, you've got all the developer services. So you could either have a traditional sorts of Cray programming environment with all of the tools that we've traditionally had on our system and runtimes and libraries, et cetera. And then you can also have analytics environments. The Eureka Manager is code that allows you to sort of dynamically choose which pieces of software you're going to want to instantiate, which collections of machine learning frameworks, et cetera. And then all the associated libraries and frameworks are available there. Lastly, this is just a picture that many of you have probably seen before. I won't go through this in any detail, but the full suite of traditional HPC developer software is there, from programming languages and models through a full sets of libraries, a really nice set of tools that we continue to crank on over the years, as well as a new set of analytics software. So let me summarize. We're entering a new era that's really interesting for all of us. Not only because we've finally gotten to exaflop, took a little bit longer than we thought it was going to take, but we're finally there. But all the stuff that's going on with AI and analytics and data-centric computing. It's a pretty interesting time to be a system architect and a user. Hugely growing complexity of managing all this data, but there's so much opportunity to extract value there, and we really think that we need a new infrastructure that's designed for this heterogeneous era. That's what we've tried to do in Shasta. We have tried to make it really flexible because you can't predict what's happening 3 years out, much less what's happening 5 to 10 years out. We've tried to make both the hardware and the software stack much more extensible than they have been in the past. The goal really is for the Shasta infrastructure to be able to last a decade or more. We can scale it all the way up to Exascale, obviously, but also we're really trying to scale down in some of the packaging choices down to a single air-cooled rack to take HPC technologies to places that we've never been able to take them before with our more specialized infrastructure. In all of this, we're trying to make it much more standards-based because increasingly the world is interconnected, and interoperability we think is really important. We think Ethernet is the right physical networking standard, and we're trying to use open APIs for all the rest of the system services to fit much more seamlessly into a cloud-like environment, support multi-tenancy, support hybrid cloud environments, et cetera, and then create that same sort of software environment that's very dynamic so you can instantiate things onto the system. And anything you can run on your laptop, you want to be able to run on the Cray. And we're even talking about taking the Cray programming environment and putting it in the cloud so you can run it on your laptop or in the public cloud. So that interoperability is really important. That's it, and I have 3 seconds left, so thanks for your attention. Do we have time for any questions?
Yeah, we have a couple of minutes for questions if people have follow-ups.
Oh yeah, could you just talk about Open API itself and the role that you think that's going to play?
Yeah, so we're basically we want to support it. We are not going to be dictating what our users do. So for the most part, we don't feel like we should be the driver in trying to tell users, what programming models that they ought to use. But we're supportive of it. I'll just leave it at that.
Good. Let's thank Steve again.
All right. All right. Thanks.